So, I'm going to talk about decoders and encoders. And I suspect this is a fairly popular part of the whole thing because I did see some questions about those in the early talks. I'll just come with a bit of caveat. There won't be much code here. This is more of a description how everything works together rather than showing a lot of code. This is partly due to time limitations. We don't have an endless amount of time, so going over a lot of code is difficult. With no further ado, what am I going to talk about? I'm going to talk about what are these things? What are decoders and encoders? What are the supported OpenSSL object types? What sort of extensibility do we have for this to support further types in the future? What is byte-oriented data? Talking about the decoding process and decoders, and the same way about encoding process and encoders. And then I'll show an example of a decoder chain, really, or rather a mesh. And I'll talk a bit about provider-side object abstractions, the relationship with OSSL store, which is kind of a bit of magic. And I'll finish with the naming and property scheme we use to identify and select decoders and encoders, and quick about the mechanics of the decoders and encoders. And here's basically the one place where we'll see a little bit of code, the type diff. So, what are these things? Well, decoders and encoders are essentially translation units. They translate from decoders. They translate from some block of byte-oriented data to another block of byte-oriented data. And ultimately, it's supposed to end up as an OpenSSL object. In this case, the supported OpenSSL object, I'll talk a little more about it later, is EVPP key. Encoders, they work in the other direction. They start from an OpenSSL object and convert that to some sort of byte-oriented data, which ultimately ends up as a block of data that the caller asked for. Oh, hey, here's a bit of code, well, at least the declaration. From the application or libcrypto's point of view, these are the functions that actually end up being called. I won't go very deeply into what everything here means because it's a seminar of its own almost. But suffice to say that this indicates what OpenSSL object type are currently supported for encoding and decoding, and that's the EVPP key. And this is tied to the fact that the only OpenSSL object type for which there is a provider native part, i.e. the opaque part that Thomas talked about in his key management talk, is the EVPP key, i.e. an object governed by a key management implementation. So someday we may have other OpenSSL object types defined as with provider native data. And whenever that happens, there will also be decoding and encoding support for those object types. We have a lot of generic OSSL decoder and an OSSL encoder functionality that is there just to be able to support all this. to be able to support object type agnostic functionality, so to say. I've mentioned byte-oriented data earlier, and that's basically almost everything that decoding and encoding is about. Byte-oriented data can be all sorts of things, let's say. It's byte encoded blocks of data for whatever object we happen to be interested in. And they can look different. They can be actual bytes. They can be an alternative encoding of the same byte. A very current example is ASCII armoring. For example, converting into base 64 is ASCII armoring. The data can be wrapped in more data. For example, the PKCS8 structure, which is a wrapping around private keys with additional data to say what kind of key is this and are the extra parameters. And it can be a little both. For example, PEM is both. It is ASCII armoring, but it's also a header that tells what type of data is inside this base 64 junk. Junk is maybe not the right word for a private key. And this can be combined. So, for example, a PEM blob can have the header type private key, and that's an indication that the base 64 bits of it, when you decode it into raw bytes, it's a PKCS8 structure encoded in a DIR encoding. That in turn is wrapping around key pair type info and data that is structured in a way that's specific to that specific key type. That's quite a mouthful just thinking about that. So we have a decoding process, and most of it is happening in libcrypto. It has been implemented in such a way that for the provider author, there should be as little as possible that needs to be written. So how all the different things like ASCII armoring, wrapping in PKCS8, all that, except that there's a decoder doing the most internal of it, tying all that together. That's libcrypto's job. It's the decoding process it does, where it ties all these bits together. And I'll talk a little bit more about how what that may look like later. But as I said, this is work that is done with help of one or more decoders. That just a little component on the way. Each of these decoders, they do some small step in the process. They can unwrap a PKCS8 structured DIR into type-specific DIR. They can do a larger step. They can go directly from, unwrapping PEM input and get it to the point that we have a provided native object without going through all the steps in between. You can also take a chunk of that process in one go. For example, doing from unwrapping PEM private key and unwrapping the PKCS8 structure in one go and leave the rest to happen by someone else. So, like I said earlier, the whole process is done by combining available decoders and calling them in a chain-oriented fashion. So, one decoder gets called, does its thing, and from that data, it's figured out which should the next decoder be, and call that one. And if there is a decoder somewhere that says, I don't recognize this input, I have no idea what to do with this, there's also a functionality to backtrack one step and try another decoder that says it can decode approximately the same sort of stuff. Each little decoder may uncover extra information about its content. So, for example, you can know from input that this is just dir data, or is assumed to be dir data. And a small decoder that successfully decodes that dir data can also, from looking at it, figure out that, oh, I have this extra bit of information. It's this structure, it's a PKCSH structure, for example, and adds that information to the context that it then passes on to the process. Calling the decoder itself, making them part of the process, a decoder can result in one of three different states. One is that the stream of byte it got as input was recognized and decoded. And it simply passes the result to the next decoder or to an object creator. If the result becomes a provider native object, like that can be governed by key management, then a key management creator, EVPP key creator, is called in the end. The next option is that the stream of byte was not recognized. And this is fine. What should happen in this case is what I talked about earlier, doing the backtracking, i.e., try another provider with the same input and see what happens. The third possibility is that there may be some sort of fatal error. The bytes couldn't be read from the input at all, like there's a reading error, permission denied, or something like that. Or we could, if we want to store some data in the heap, and malloc or OpenSSL malloc fails because we're out of memory, this is also a fatal error, and that aborts the whole decoding process. So no more decoders are called after that. There's a similar, although a bit easier, encoding process. This is the one that translates from an OpenSSL object like EVPP key, or rather its provider native part, to some desired byte-oriented data, i.e., someone has made a call saying, hey, I want this EVPP key to become a PEM file over there. Or to be text output. That is also part of encoding. That's why I including human readable text. And it does this in a similar fashion with the help of one or more encoders. And just like decoders, each encoder can do a small bit of the process if they want to. Like they get some type-specific dir, they get the information of what type of data is in there, and they produce a PKCSH structure, wrap it in the PKCSH structure, and leave that result to the next encoder. They can do larger steps, like going directly from provider native object all the way to PEM, and all that needs to be done with that is save it to file or anywhere. And they can do anything in between those. And the process is done in a similar fashion by combining a series of encoders and calling them in a chain-oriented fashion. The encoders themselves, they can only result in two states. Either the encoding was successful, passed on to somewhere, and the process continues, or it was not successful for any reason, like it couldn't be encoded, or writing to whatever place we want to get the result was not possible for any reason, and things like that, and that aborts the process. The title says decoder and encoder chains, but I'm sticking with just decoders. You will see the same sort of mesh with encoders. So this is a possible view of available decoders and what they result in and how that builds a chain. So for example, most of these we have implemented in OpenSSL exactly like this. So they are really small components with which you build a chain. The two bottom ones do not exist in OpenSSL, and I hope never anywhere, because I really hope that no one implements the Blarg algorithm. They are just an example to show that any provider can provide any sort of decoder, and conversely encoder in that case. And these show two decoders that do the large step, that go directly from PEM or what's called JWT, that Java something, I don't remember what it's called, to an EVPP key of the Blarg algorithm. But as you can see by following the arrows, you can also do the whole chain thing. Like you can go from the PEM to DIR decoder that then gets passed on to the DIR PKCS8 to DIR type specific decoder that will attempt to see, is this a PKCS8 DIR that I'm getting in? Okay, I can unwrap this. This is cool. If it's something else, it will just say, no, I don't recognize it, and the process will then possibly try the next one, which is DIR subject public key info. And if that one doesn't fail, it will try the other ones as well, those type specific, to see if the PEM decoded into something that's more type specific and not wrapped by PKCS8 or subject public key info. Ultimately, it should end up as an EVPP key. And this is done, that last step is done by constructing an EVPP key from a key management, with a key management that corresponds to the output from the last step, i.e. these things, RSA, DH, EC, Blarg. It goes looking for a key management with the same name and constructs an EVPP key using that and whatever data was passed from the last decoder. This was a lot. Moving on. The decoders, to be able to specify what kind of data it actually decoded, it passes on a, it is supposed to pass on a provider object abstraction, is what we call them. There is a manual for it. I have put references to it at the end of this talk. And this is an abstraction that's entirely in OSSL param form. And encoders may use the same sort of abstraction as input. So this abstraction contains the object data in itself, in whatever form it happens to be right for the moment in this decoder or in this encoder. So it can be raw bytes if the decoder if a decoding step ended up with dir, with a bunch of dir encoded data, this abstraction will have a pointer to those raw bytes. It can additionally contain information on what OpenSSL object types the data is suitable for, and it does cover more than EVPP key, as I'm listing here. It also covers X509, X509 CRL, etc. And this is connected to a bit of trickery that I'm going to talk about a little later. When we're just decoding to an EVPP key, it's expected that the object type will be EVPP key, or will indicate that EVPP key should be the end result. And there's more information about what object content, what the object contents are, if it's dir, if it's an RSA key, if it's a DH key, if it's an EC key, all that sort of things. So that coming out from a decoder, we're passing on as much data as possible, as much information as possible to the next step to be able to do this job. And also for the decoding and decoding process, to be able to figure out which one should we call next. Here comes a bit of magic. OSSL store is kind of sort of involved in this. Specifically, it's the OpenSSL's file store backend, i.e. the one that knows how to read all sorts of files, PEM files, raw dir files are the ones that are currently handled by OpenSSL providers. It basically, what it does is that the OSSL store backend has a bit of extra magic. It uses all decoders that it can get its hands on, and it adds its own fallback decoder that will make a provider object abstraction for whatever data it took out, where it will say, I actually don't know what object type this is, but I'm still passing it on. I'm still saying, yeah, I could decode something that was dir encoded, is the current implementation. And I'm just passing that on and just saying that whatever the next step is, we'll have to take care of it somehow. And decoders, they pass on data to whatever the next step is by calling a callback that it's being provided. And the OSSL store library has a fairly special result handler that works as such a callback. So that one knows that it's going to get an object abstraction of some sort, and knows that if it gets one with the object type unknown, it goes trying to do some more decoding of its own. And it knows much more than the providers have any chance to know, i.e. it knows about X509s, it knows about X509 CRL, it knows about all the types of stuff that libcrypto has knowledge of. So what it does is that it basically takes over. It says, okay, I'm pretty sure I've gotten a bunch of dir here, and I'll try everything I have knowledge of. Totally separate from the providers. And that's where the information about OpenSSL object type that I'm mentioning here that says, talks about EVPP key, X509, X509, CRL, etc., comes in, there is a possibility going forward that this can actually be mentioned already from providers as soon as they start having that sort of support, which may or may not happen in the future. We currently do not know. To be able to connect all of this, to be able to figure out which decoder should be called next and what are they producing, we're using algorithm names for decoders and encoders, and we are using properties. One of them is used to express what sort of input do we expect. The other is to express what sort of output is expressed by this specific decoder. And they are, decoders and encoders are doing it in opposite ways from each other. And I'll come to that now next. For decoders, the algorithm name, and now that when I'm talking about algorithms, is their specification in an OSSL algorithm array. So there is a decoder operation. And the algorithm name reflects the output of a decoder. So if there is a decoder with the algorithm name dir, it's expected to output dir, a dir blob, a bunch of bytes that is a complete dir object. If it says something like DSA or RSA, it's expected to have the output a ready-made provider native RSA key that can be just associated with a key management from the same provider. Properties reflect the input of the decoder. So if a decoder wants to express that it takes dir as input, then it says this with input equal dir. And if it wants to specify that it takes a specific, that it handles a specific structure within that dir blob, for example, a subject public key info, then it can say that as well with structure equals subject public key info. Then it's expecting that the content that it's getting as input is wrapped in a subject public key info structure. Encoders work approximately the same name, but the other way around. So in this case, the algorithm name for an encoder expresses the input that it's expecting. So an encoder that encodes an RSA key in provider native form is named RSA. Then you know that, if you have an RSA key, that's the encoder to go for. And then it uses properties to reflect the output that it provides. For example, in this case, output equal dir says that this encoder will give us a dir blob as output. And it can also mention a structure saying that this is the structure that this encoder will use for its dir output. Now we're coming to the last bits, and this is the actual mechanics. The decoders are really implemented with a number of other functions. The rest of the functions are more or less fluff that you recognize from other operations, like you're creating a CTX, you're freeing a CTX for that implementation. you can get and set params. I think you can do that, and a few other things. The interesting bit, though, is this function, the decode function itself. What it does is that it takes input data via a bio. And I will quickly mention that the OSSL core bio is a bio that is mapped back to the calling libcrypto. It does a little bit of magic somewhere in there so that we don't have different internal bio data happening, getting across from provider to libcrypto, where both ends have different ideas of the internals of bio. So it's kind of a magic thing that does a little bit of bio translation under the hood. It can be used just as a normal BIOS by providers, I mean. So that's where a decoder reads data from, and then it does something with that data it's been reading, and it will create a project object, provider object abstraction, and pass that to the data callback that you see over here, data CB. And I actually mentioned that on the next page a little more. So this is what calling a decoder results in. And remember what I said earlier, that basically it has 3 result states, and they are made in a combination of calling the callback or not and the return value from this decode. And do notice that it returns an int, so it's essentially a Boolean. So the 3 states, if data reading errors or there's some other fatal error, it returns 0. If the data was read correctly but was not recognized, i.e. you could read bytes but you couldn't recognize what it was, i.e. parsing the data was unsuccessful, the decoder should return 1. And the reason for this differentiation is that when a decoder returns 0, the whole decoding process will be aborted immediately because something is badly wrong. While when it returns 1, the decoding process will take that as a signal that, oh, okay, let's try another decoder with the same input data, i.e. with the same bio, which is backtracked to the same point that started this particular decoding call. The third option is that the data was recognized, and then the decoder creates a provider object abstraction, populates it, I forgot to write that, with whatever the decoder has figured out, calls the callback with it, and returns whatever the callback returned. And that last bit means that because of the way this works, the callback is some code in libcrypto that is then responsible on calling the next step. So it's through that callback that the next decoder or the object creator is called. So the whole decoding process is really calls back and forth between provider and libcrypto until you have an desirable end result. So the next decoder in the chain might be the one having some kind of failure, reading error or whatever, and that returns 0. And that goes back to the decoder we're currently looking at, that returns the same thing, i.e. 0, all the way back, which is the way that the whole abortion happens. It happens by returning 0 the whole chain down. And one question that people may want to know, that I haven't written up here, is so the decoder can essentially return 1 in 2 cases. One when the data wasn't recognized, i.e. no callback and ultimately no OpenSSL object gets created. And the other one is when it's successful all the way, i.e. the callback has been called and further decoders have been called until we have an object creator that does something. The thing is that in libcrypto, the decoding process registers whenever an object creator is called. That's the ultimate end, and at that point, the library process, the decoding process won't do any more work because the ultimate goal of creating an object has been reached. And so the decoding process in libcrypto knows this the whole way down back the chain. So whenever any decoder down the chain returns 1, the decoding process in libcrypto goes looking, oh, okay, so we have information saying that we did get an object in the end. Fine, we don't need to do anything else. Let's just continue to return 1 all the way back to the caller, to the user, to the application. Or if it doesn't have the information that that final object has been created, then it will go, oh, this means that we don't have anything yet. We should try another decoder that can hopefully take the same input as we have had in this step. It's a bit complex. The mechanics for encoders is similar, but easier. This is the corresponding encoding function that it takes one of 2 possible arguments as input. Either it has raw data, which is the provider native object, and this is something that it's expected to know exactly. It's not opaque to this particular encoder. It knows exactly what the contents look like because it's native to the provider that implements this encoder. The other sort of data you can get is an object. It's a provider object abstraction, and the encoder should know how to handle this. If you get an object raw, it knows how to handle it. If you get an object abstraction, it knows how to handle it and to produce some kind of encoding from it. And what it does is that it works out some sort of encoding of this input and simply writes that to the output bio out. And for encoders, there's just 2 possible results. Either the input could be encoded and the result was successfully written to out, then it returns 1. Or either input could not be encoded because something was wrong with it, or writing to out failed for some reason, or there was some other error, it returns 0. And this has, in the encoding process, approximately the same effect as for the decoding process, i.e., if it returns 1, then the process continues. If it returns 0, then the process is aborted. A word, though, on the process continues, because we just wrote to a bio. It's just that in libcrypto, the encoding process will give each encoder a pointer to a memory bio. And so whatever is written to this out actually ends up in memory somewhere. And the encoding process will then wrap that in some sort of object abstract and pass that on to the next encoder with a new memory bio that gets written to, etc., until we reach an end somewhere where the output of that encoder is what the user, the application desired. Then that output is written directly to whatever file, whatever bio the application passed on. This is also a bit complex, a bit less than decoders. Like I said, I don't have much code, because going through actual code, first, I unfortunately lacked the time to write a short enough encoder or decoder to show as an example. And this does need a bit of reading manuals. These 3 manuals are the ones to start with. To write decoders, to write encoders, and provider object is the one that describes this provider object abstraction form.